So first of all, I'd like to thank the organizers for this very nice and very interesting conference. I think I learned a lot on liquid crystals. But yeah, I'll continue today's tradition of not talking about liquid crystals, and I'll give you a short overview on our work on active colloids. And I started to talk on a brief introduction, so I'll skip the physics part because I guess you all know it better than me, because I'm actually a chemist. Then I show you a funny example of the first, some of the first artificial micromotors that are propelled by bubbles. Then I'll talk about our work on self-diffusive phoresis, and then I'll just show you our very recent project on light-driven micromotors. So some of you might have seen this movie from the 60s where people suggested to just shrink macroscale objects into the microscale, and then they used this little submarine to heal a Secret Service agent. But I guess most of you are very familiar with the physics at the microscale, so the physics prohibit just this approach. And there's a couple of things that I just want to mention that people, in order to move things on a microscale, actually have to take into account. First is that the flow conditions change if we shrink things. So if you would go to the pool and swim, everything would be relying on turbulences around you that you pass on to the surroundings. But once you shrink things, like there's no inertia anymore, and the viscous forces will dominate, so that all the flows that you would get are basically laminar flows. Another thing that makes things much more complicated is Brownian motion, because if you want to bring something from one point to the other, Brownian motion would just randomize all the directions that you would try to take. And the last point for this slide is energy, because if you think about your car, you fuel it and then you can just drive it as long as there's still fuel in the tank. But if bacteria wanted to take the same approach, they would have to carry things with them. And since they are so small, the amount of fuel that they could carry is very limited. So nature had to come up with an energy-rich reaction that enables microorganisms and microswimmers to gain energy from the surrounding. And they use this hydrolysis of ATP, so they just got rid of one of those phosphate groups, which results in this ADP, and a phosphate group and some energy that microorganisms can actually use. So but there's also a little bit of symmetry breaking involved. And so motion at the microscale is largely governed by the Navier-Stokes equation. And we just see it here, like this is taken from this paper from '77 from Purcell. You see that the time doesn't play a role in the microscale. So basically, there's no, the time doesn't bring us an asymmetry. And the example that Purcell used to explain this is actually a little animal that we've already heard about on Monday or Tuesday. It's the scallop. And what a macroscale scallop does, it's opening and closing its shell, and therefore it's creating turbulences surrounding, and that's why it's moving forward. So, but if you would shrink this little scallop to the microscale, since there's no asymmetry in time and since there are no turbulences anymore, what the scallop would achieve would be just a little bit of movement forward and a little bit of movement backwards. So that would not be an efficient propulsion, and the poor little animal would just starve. I'm not sure, have you seen this video? You have? No? You have not? Most of you have or not? Okay. Then I just briefly show it. It very nicely illustrates how things on the microscale or in low Reynolds numbers are actually not time dependent. So we have here two cylinders, the other one, and here we can see the other one. And there's a little bit of glycerol, which is a very viscous fluid. And the people from the University of Mexico, they just added 3 dots of color. And now when they turn it, we just get a shear flow, which is, you can see, mixing the droplets. So we see at the beginning we still have blue and yellow there, and after some time we just get green and a brownish stripe in the middle. But now if they stop moving in one direction and they just reverse the whole motion, then we will see in a minute basically the effect that like a microscale scallop would be experiencing. Things are totally reversible, and they just go back to their initial state if you reverse motion on the microscale. And you see, except for a little bit of diffusion, we are just back to our initial state. So, but nature, over the time of evolution, has optimized many of these little swimmers. So from ATPase nanomotors that are just like a few nanometers over the motor proteins, bacteria, algae, and sperm, like all these things are very motile and do very efficiently move in the nano and also in the microscale. And just after the year 2000, people started thinking and like really experimenting also on these kind of things to make and create this motion artificially. And here you see like one of the most used material is platinum, and here you just see like an overview of structures that have been created and that have been used for micromotion. I'll just show you very briefly those two. And let's start with one system that is quite intuitive because it works like a microscale rocket. So what you can do is you can use photolithography to pattern like little squares, then put a multi-layer of metals on top, and then when you etch this polymer away, what you get is this kind of rolls, simply because there's strain in between the different metal layers, and if they have nothing to be attached to, they would roll up just very much like this. And if the last metal layer that you have deposited here is platinum, then the inside of the roll is covered also with the platinum layer. And what happens if you give this whole thing into a peroxide fuel is that things just start moving. They produce bubbles, and these bubbles propel them forward, pretty much like a microscale rocket. So you have the bubbles that are created somewhere here, and they move throughout the tubes. They usually start by like random fluctuations in the beginning into one direction, and then they continue expelling this direction. And then it's just very basic physical principle, axial equal to reaxial. So you have thrust, and this moves the tubes, the microtubes, forward. However, most of my work has been on a system that is much simpler, and it's not so intuitive. So what we do is we use microscale colloids, just like silicon dioxide, polystyrene. It's just important that's an inert material. We deposit them in a monolayer, and then we evaporate platinum or the metals on one side of them, so that we get this Janus-type structure. And if equally to the microtube, we put them in peroxide solution, hydrogen peroxide, which is the fuel for the reaction, then this platinum surface is a catalyst, and it degrades the peroxide. So we come to water, which is just dispersing in the environment, and oxygen, which is the solute that actually builds up the gradient. So since we have this asymmetric structure here, we have much more product on the platinum side of the particle compared to the inert side, which creates a gradient and a gradient of solute, and this interacts differently with the surfaces, so that we get an osmotic pressure, which you can imagine that it's kind of pushing the particles forward. But since I can't expect you to believe me, here you actually see like there are no visible bubbles, nothing. It's just this gradient created. And sometimes they do funny things that interact with each other. There are some ways also to control and influence the behavior. And some of them are very intuitive. So for example, if you give them less fuel, they move very slowly. If you increase the fuel concentration, they can go in the same amount of time over large distances. If you want to control their orientation, what you can do is a very nice engineering trick. So my colleagues have used a multi-layer of cobalt and platinum, which enabled them to create this out-of-plane magnetization. And then if you have these particles in a magnetic field, they very well orient according to the magnetic field. And another very often cited phenomenon that you can use to orient the particles and direct them into a certain direction is chemotaxis, that would move to a higher gradient fuel concentration, or the opposite, which is the run and tumble kind of motion, which would move and end up in the lower concentration. But we have observed our particles, and just because most of you are serious, just a quick reminder. So our particles, they are density mismatched with the environment, simply because their density is higher than the density of water. So the silica part has a density of 2, the other one has about a density of 20. So we have a difference even in the two sides, which we call bottom heavy. So if we just have these particles in water and we don't have any active compounds, then what we see in a microscope is just these black circles, simply because the platinum would orient cap down and absorb all the light, so we see just simply black circles. But once we add peroxide, the particles get activated. They change their orientation, so that depending if you're a person who thinks in a real world or in a vector world, this is a 90 or a 0 degree orientation. And we basically see half a cap and half a inert cap. And we thought, okay, if the particles do this all the time on the substrate, right, they always orient like this, what happens if we just try to put a wall in front of them? Will they show the same kind of behavior and therefore enable us to really guide their trajectories? So this behavior would be very analogous to what actually motor proteins do in order to overcome Brownian motion. So we just used a photolithographical technique to pattern these stripes into our silicon wafer, and we could observe that the particles, once they bump randomly into the wall, they start orienting, and once they have reached this 90 degrees orientation, they just follow the straight walls. This work was done at the MPI in Stuttgart, and we had a lot of theoretical collaborations. And they also made some models for it, and they could show that basically when we're in a planar wall, and also when we're in a vertical wall, the model is basically the same, just that here they had to also introduce gravity. So at any orientation and at any given height that we put the particles, they would always converge to these stable points that are at these 90-degree angles. So, but this was still relatively easy, right? So the particles just had to bump into the wall and then follow a straight line. So we thought, okay, we'll increase the level of difficulty. And we basically gave them round pots, still just structures in the silicon bottom. And we checked if they can move. And you see that they can actually also follow these round structures, which is remarkable, simply because the particles have to orient and adapt their orientations at every given moment of time. And these structures also enable us to study how the behavior evolve over fuel concentration. And we found that the more fuel they have, the longer they actually stick to the structures, which means that the origin of this behavior is somewhere lying in the phoresis of the particle. Here you have already seen that two particles, when they by chance meet on the same pot, then sometimes they kind of do funny things with each other, and we'll see more of this in a moment. So, question? Sometimes they would get stuck, but sometimes they manage to. You would have to really tune the distance that they can. but like the attraction forces are relatively short-ranged. So you can't just, you will really have to meet exactly the distance of the particles so that they can switch from one to the other. So if we don't have POS, but if we have motile particles, we can still observe very similar effects, so that you basically see that the particles can move around these. But here you have seen that it's really a short-range attraction. It's the particle could just pass by and not see this kind of POS. And this even works if the passive particles are much, much smaller. As you see here, this is just like below a micron, but it still manages to change the trajectory of the other one. And here we actually see something very similar, because if two particles get stuck on these, they can form like these little triangular structures and move in a pretty directional way. With this system, we cannot, simply because most of the particles, their density mismatched. So it would cost them quite a large amount of energy to climb. But right at the end, I'll show you that in some cases we can actually get them in a slight, like not in a monolayer, but in a B-layer. But a real 3D is simply because of this mismatch of the density. It's not so easy. Yeah, so here we could see that these structures, even though they have formed, they are not rigid objects, so they can still be disassembled by any kind of events. And here we see that they can even synchronize, which is a phenomenon very much studied in algae to understand the swimming and, for example, the coordination between two flagella. So, but if we do not just use round objects, we can also achieve like much more funny effects there. So if we tune the shape or the geometry of the object that we give our particles to play with, and we have something like this gear here, if one of the sides of the arms of the gear is short enough that the particles can't really dock in there, but the other side is long enough that the particle can like really swim in here and orient, then we can achieve a structure that can be very well rotated by our particles. So here you see that if you have one particle rotating here, it's quite slow. Two is a bit faster. This guy also showed that the interactions also here were pretty much short-ranged. And if you wait for long enough and you observe the particles self-assembling, then if you're lucky and patient enough, you can see this very nice assembly. And I mean, this seems to be quite like just a toy, like something to play around with. But if you actually think about it, if you want to rotate this kind of passive structure on a microscale, then you would need a polarized optical tweezer that costs several thousand of euros. And we could do this just with a little drop, like a glass slide, a little drop of particles, and a little drop of peroxide. And the microscope is nice because otherwise, yeah, they might rotate, but you don't see it. And actually, like this experiment was inspired by this previous experiment of the group of Roberto di Leonardo in Rome. And you see that many things, like even the artificial microswimmers, they behave very similar to the natural ones, because many of the behaviors of these bacteria, they are simply governed by hydrodynamics, which is also the case for our microswimmers. So, but most of these systems that like all of these systems that you have seen by now, they were all relying on peroxide as fuel. And peroxide is very toxic. So if you want to go into applications and if you really want to do something with the systems that you're creating, then you should somehow get rid of peroxide. So we thought, okay, we have to change the material. And we moved to titanium dioxide. So we made them, depending on how we calcinate them, they get different morphologies. and we decided to use the black ones. But why titanium dioxide? Titanium dioxide is a semiconductor with a band gap of around 3. So if you shine UV light on it, what's happening to the electrons that are just within the material is they get promoted from their valence band to the conduction band. And this promotion, what it causes is that we have a pair of a reactive electron and the reactive hole. And if we have this reactive pair of particles, then we can create chemical reactions. And if we just use, as before, hydrogen dioxide, then what we can do, like we can degrade it into peroxide, into water and oxygen, just as before. However, this system also enables us to work simply with water, so to get really rid of this toxic fuel, degrading the water into hydrogen and oxygen, which is still thermodynamically inhibited. So what comes in handy is to evaporate a metal layer on one of the halves, which also is kind of practical if you want to achieve motion of the microscale, because you get rid of your symmetric system and you introduce some asymmetry, which, as we've seen before, breaks the symmetry that's not there through time. So when we use our titanium copper particles, we can use them in 3 different conditions. We can use them in water with UV light, with very energetically rich UV light, but we can also use them in peroxide with just yellow light, or we can use them in peroxide with UV light, and they will have different speeds of motion. Obviously, if we give them a very energy-rich fuel and an energy-rich source of light, then they move much faster than in the other 2 conditions. And then what we've been doing is we have probed the fields that are formed around our particles by adding simple passive particles. And what you see is that in the different conditions, they do interact very differently. So if we turn on the UV light here, this is in water, we see that our particles do move, but they don't want to know much about the passive ones. They much rather interact with each other, so that after some time, what we observe are these clustering events, where all the black active particles, they stick together, and they do kind of a pumping behavior, and move the passive particles around them. If we exchange the fuel, but we stick to UV light, you see that our particles themselves, they are much faster, but they also do interact very differently with the passives. So you see that they can really move them around, and they actually also assemble in these hexagonal structures. You just saw that they shifted. Like here's a very fast one. So you see that they organize in these hexagonal patterns, and here you also see these round dots on top. These are actually the 2D assembly. But still, like the material is quite density mismatched, so it's not a real 3D structure. I've done experiments using deuterium and using polystyrene, but when there's no substrate, they don't swim very nicely. So I have already almost reached my conclusions. So we can make artificial micromotors that swim through catalytic reactions. We can influence and direct their behavior through monitoring and modifying the environment, which can up to lead to the movement of passive objects. And we created like ultra-fast titanium dioxide particles that swim in different fuels and with different energy sources. And just as a little add-on, we have seen that nature has optimized swimmers quite a bit. So things like bacteria, they swim, they can adapt to many different surroundings. They are very flexible. And if you actually look at your own body, like up to 3% of your own body weight are actual bacteria. So we thought, okay, why shouldn't we just take benefit of the optimization of nature and just try to make hybrid structures? So what we found was that the bacteria actually very much like the metal part of our bacteria, of our particles. And so we tried different materials. They really very reliably stick to the metal part of them. And we could even show that the bacteria, like even though you see that the bacteria is much smaller than the particle it's going to move, they can still really drag them. What is kind of intuitive is that if you compare the speed of a free bacteria to the bacteria with a tiny bead like this here, it gets a bit slower, but if you put like this huge bead on the small bacteria, then it slows down quite a bit. Yeah, this is just for you to see. So yeah, I would like to thank my current group in Dresden, my former group in Stuttgart, and yeah, obviously our funding sources. So yeah, happy to answer any questions, and if not, thank you for the attention.